This Exercise 101D is an extension of Exercise 101C, where we now perform a 3D finite element analysis of the same rectangular plate under compressive static loading. The plate is subjected to a compressive load of 6 kilonewtons in the x direction to evaluate the margin for buckling. One end of the plate is fixed to represent a clamped boundary condition, while the compressive load is applied at the opposite free end, simulating a fixed free configuration. The steps in performing the FE analysis are shown here. The first 3 steps of geometry, generating the mesh, and assigning material and element properties are the same as those already covered in Exercise 101B, so will not be repeated here. Focus in this video is specifically on the buckling analysis in steps 4 to 6. This step demonstrates how to set up a buckle step for the analysis in Exercise 101D. The step type is changed to buckle step, and the number of buckling factors is set to 4, meaning the software will calculate the first 4 buckling modes. All other boundary conditions can be defined the same way as shown earlier in Exercise 101B. In this step, a compressive load is applied to the plate by creating a concentrated force at the reference point, which is connected to the loaded face of the plate via a rigid body constraint. Although the actual problem specifies a compressive load of 6 kilonewtons, only 1 newton is applied in the finite element model. This is intentional and acceptable for a linear buckling analysis, where the results are expressed in terms of a buckling factor. The buckling factor represents how many times the applied load, in this case 1 newton, needs to be scaled up to reach the critical buckling load. Therefore, the choice of 1 newton acts as a unit load and simplifies post-processing, allowing us to easily calculate the actual buckling capacity of the structure by multiplying the buckling factor with this reference load. After defining the load, the setup is complete and the model is ready to proceed to step 5, where the analysis is run to extract the buckling modes. After running the buckling analysis, the software provides multiple buckling modes along with their corresponding buckling factors. Go to the Results section and navigate to Buckling Factor under History Outputs. This will display the calculated buckling factors in the table. In this analysis, we have requested the first 4 buckling modes, and the software returns the corresponding buckling factors. These values indicate the load multipliers at which buckling is expected to occur for each mode. To visualize the deformation shape for each buckling mode, we use the Step Increment dropdown at the top toolbar. By changing the increment, we can view different buckling mode shapes. On the next slide, we will explore how each of these modes looks and interpret their deformation patterns. Here we can see the different buckling mode shapes corresponding to the buckling factors we observed earlier. Each image represents a mode shape, and the associated buckling factor is shown at the top of each plot. These mode shapes help us understand how the structure is likely to deform when buckling occurs at the respective load multiplier. Mode 1 buckling factor, Mode 2 buckling factor, Mode 3 buckling factor, Mode 4 buckling factor. To switch between these modes, we use the drop-down menu in the post-processing toolbar, as shown in the previous slide. This slide presents the validation step, where hand calculations are compared with finite element FE results to assess the buckling behavior of a plate under compressive loading. The plate's dimensions, material properties, and boundary conditions, fixed free, are clearly defined. Using classical Euler buckling theory, an analytical calculation is performed to estimate the critical buckling load. This includes applying a fixity coefficient appropriate for a fixed free boundary condition and calculating the moment of inertia based on the plate's cross-section. The resulting allowable buckling load is found to be 1,628 newtons. Since this is significantly lower than the applied compressive load of 6,000 newtons, the reserve factor, an indication of how close the structure is to failure, is just 0.271. On the other hand, the FE analysis is conducted using a buckling simulation setup, and the first buckling mode yields a buckling factor of approximately 1,657.2 newtons. This result is very close to the hand-calculated value, indicating a strong correlation between the theoretical and numerical methods.